Okay, back in part 2 of this little mini lecture on chapter 14, I got cut off talking about this last number here, 1200 floors. How did I get that? Again, we were talking about the energy in the M&Ms being the number of calories times 4186, and that's 2,100,000 joules equal to mgh, because we're going to put it into climbing stairs. Comes out to be around somewhere around 3,600 for a 60 kilogram person. That 3 meters per floor, right? It's about a little, just under 10 feet per level or floor of a building. 1,200 floors. You know, you're talking about going up the Empire State Building like 10 times. Now that is crazy to think. If I just eat that innocent little bag of peanut M&Ms, that I would have to climb the Empire State Building 10 times to burn it off. Makes you think about eating that stuff before you do it, actually, doesn't it? But we do. This is 100% conversion from that to PE. We lose a lot of heat as we're walking up the steps, right? We lose a lot of heat from our body, and our body isn't 100% efficient in converting that stored food into going into actual energy. Now we could have also done one and set it equal to half mv squared just to laugh about how fast it should make me go if it was, again, 100% converted, which it won't be, but if it could be, how fast would it make it go? We can play little numbers there. So it's kind of silly there, but we understand what's going on there. Now I want to come back to this number up here about the 4186, and what it's telling us is that 1 kcal, 4186 joules, let me get a different color here, this actually would heat up 1 kilogram of water 1 degree centigrade. So if I had that many joules of energy and I put it directly into water, 1 kilogram of water, it would raise the temperature by 1 degree centigrade. And opposite, if I took that much out, it would reduce the temperature by 1 degree. Okay? So how much, let's look further at this conversion. So what I'm going to do is clear out this and bring up a clean sheet, I think. Let me try that again. And what is the relationship between heat and change in temperature? Well, it's pretty obvious that if we add heat, the result is that we increase temperature. If we remove heat, cool something, we reduce the temperature. So we can see that they are related proportionally. It would also see that the amount of mass we have, or how much stuff we have, would affect that. All right? The more mass we have, the more heat we would need, and the less mass we have would also mean the less heat we would need to heat it up. And we also see it depends on the material. Okay? Water takes a lot longer to heat up than just an empty pot. So if we take all those together and those relationships and put them into an equation, we get this equation. Q equals mc delta T. Now Q is heat, still in joules. M is going to be the mass, that's always in kilograms. Change in temperature is in Celsius, and we have this C value. C is known as the specific heat value. Chemistry folks, you've probably seen this. Specific heat is, in my mind, or the way to think of it, is a form of temperature inertia. There's that word again, I can't get away from it. Inertia, again, is a resistance to either move or stop moving. If it's temperature inertia, it would follow then that something with a high temperature inertia means it's very slow to heat up and very slow to cool down. So something that has a big specific heat value is water. It actually has one of the highest. Okay? 4186 is its number. If I use something like iron, which will heat up quickly and cool off quickly, it's only 450. So we're going to need to continue this again in the next video, but that gets us into looking about that relationship. So stick on for the part